Hi everybody, I'm Hedayat Alghassi. I'm a researcher in Carnegie Mellon University working with Professor Sritar Tayur. This work is about Graver basis, calculation of the Graver basis using the quantum annealer and also using this Graver basis in nonlinear integer optimization problems. Initially, I go through the motivation of the work and then talk about the Graver basis in some details and then how we calculate the Graver basis, how we use it in the nonlinear integer optimization problems, and how we can surpass the best-in-class classical solvers. As you know, a naive version of solving the Graver, solving nonlinear integer optimization problems is solving this minimum f of x, ax equal to b. F of x can be any type of problem, quadratic or polynomial or even or radicals or every shape. We have to, the naive version is convert the non-quadratic f of x to a quadratic one, which needs extra variables, and then add the constraint to the quadratic part and solve this one, which is not a really good idea. We want to do something else. We want to come up with something else. There is a concept in classical optimization problems, it's called test set-based optimization. Means we have a main quadratic and then we have some basis. We start from one feasible solution and we add the basis elements to it one by one, and wherever we see that we are improving the cost, we chose that one. When we reach to a point that by choosing all of the elements in the base, we don't have any improvement, there is a proof that we have reached to the global solution. All of those test sets which have this property is called optimality certificates. One of them is the Grobner basis, which basically all the concepts started from University of Innsbruck by Grobner, Professor Grobner, and then Bachberger, who got his PhD in this university. But the test sets that we are using is due to Graver. We have two definitions here. A lattice integral integer kernel of a matrix A is all the integer vectors that satisfy AX equal to 0. We deduct 0 because 0 is a dummy solution and we don't want to have that among the, for our definitions. A partial order between two vectors X and Y basically is the fact that first, both vectors have to have the same sign. Means both of them have to be on the same orthant. Orthant is the generalization of the quadrant. And then absolute value of the one, if absolute value of the one is less than absolute value of the other on all of the elements, then we can say X is conformal or conformal minimal to Y, and we show it with that term. So this is an example. 1, 0, minus 1, 3, 0, minus 2. Both of them are on the same orthant because both of them have the same sign. So X is conformal to Y, and absolute value of elements of the X is less than absolute value of element of Y. In the second case, they're not in the same orthant. They don't have the same sign, so they're not comparable. On the third case, they are on the same orthant, but absolute value of the elements of one is not lesser, so they are not conformal to each other. So we have generally three cases that comes up with two conclusions. Either they are conformal or not conformal. So Graver basis is all the vectors inside the kernel of a matrix A which are conformal. All the conformal minimal ones means all of the elements, when you compare them to each other, none of them are conformal minimum to other. The number of the elements of vectors in this lattice vector is finite. So there is a proof for that. It's called Gordon lemma. So what is this is an example of a Graver basis. Our matrix is 1, 2, 1, and then 2 minus 1, 0. 1, 0, minus 1, 0, 1, and minus 2, and the symmetries, the minus of each of them are among the Graver bases. Also 1 minus 1, 1 is the Graver base. If you can check all of these, you can see that either they are on different orthons, or if they are in the same orthon, they are not conformal minimal to each other. So, Graver in 1975 proved that this basis can optimize linear system, linear integer programming system, means f of x is c of s, ax equal to b. Later on, people have proved that we can use it for many other optimization problems like max of fwx, separable convex functions, all of the norm type of cost functions, some of the quadratic functions, not the quadratic convex ones, some of the polynomial functions, not all of the non-convex versions. Most of them are convex or separable convex. So there are a bunch of cost functions that we can use, and there is a proof for that, that with polynomial number of iteration, we can reach the global solutions. So we want to use this. So we say, we are using this approach, but calculation of the Graver basis is computationally expensive, very expensive, if the matrix A is a general matrix, like random matrices. So we want to calculate that. How we do this? We are using a quantum classical approach. In the first run, we use the quantum computer to find all of the lattice elements in the area that is interested, in the area of feasibility. And then we do classically compare them with each other, and we basically check that conformal minimal part classically in the second stage. And we repeat these two in the next calls while we try to adjust the variables appropriately so that we hunt more variables, more vectors during the next calls. How we do it, I'll talk about that. So for the Graver basis, we need a cubo ax equal to 0. Basically, the cubo for that A is A transpose A in the integer domain. We need integer to binary transformation. We can use binary encoding or unary encoding for each of them. You can go through this on the paper. It's pretty easy. So, but the point is, we start with lower bound of each of these encodings, and also we adjust also the encoding length for each of the variables. We adjust this in our formulation so that we can adaptively change it in the next iteration based on the results from the previous iteration. So the whole concept of this idea is based on this fact, which might be wrong, that we assume that D-wave or any quantum annealer is a uniform sampler of at least states, initial states, not the results. And then, so based on that we start, and we ask for many calls in a maximum number of the calls in each, maximum number of anneals per each call. That's why I ask why we cannot increase the number of calls from 10,000 to, let's say, 100,000. Because for when we want to have many solutions, we need that. So also, we assume that our cubo has symmetry. And also we do some techniques like changing the, permute the columns so that our cubo in the next iteration becomes more and more symmetric and we hunt more of the variables. So after running through the D-wave, we observe that majority of the non-optimal solutions that we are acquiring are pretty close to optimal. There's suboptimal. The error for majority of them is about 1 or 2 or 3. Some of the error is around 1, 2, or 3. So we decided to do another layer of post-processing on the results. And this layer of post-processing is very systematic and structured. So the complexity of this post-processing is low. But when we do this post-processing, at the end of the post-processing, we have more percentage of the solutions of our kernel. So this is one example, 4-coin problem, which is pretty famous on the context. In one call of D-wave with encoding bit of 4, with one call of D-wave, we end up with all of the gray bases. In this one, which is pretty harder because all of the elements in the matrix are prime numbers, we end up to extract all of the gray bases in 3 calls. In binary matrices, though, we have more luck, and let's say in this example, in one call, we extract all of the gray bases, 106 gray bases. But when we randomly change the binary matrix in this specific size, we have to do more calls and adaptively changing the starting point of the encoding and the width of the encoding. So how we use this gray basis in an optimization problem? It's pretty simple. On the test set-based optimization, I told you that we need a feasible solution first, and then from that feasible solution, we have to go down and find the problem. So we have to also solve AX equal to B to find the feasible solution in the area between a lower bound and upper bound. This is the QBO for that. But the good news is when we call this to D-Wave, we have many solutions instead of one. And the choice of which solution to choose for feasible solutions basically is one of the things that we can consider. So the basic algorithm is that use the gray basis, which is a quantum classical system for and calculate the gray basis of the matrix, and then find basically a feasible solution, and then do the augmentation, which is completely classical. And you can do it for any cost function, any shape of the cost function. Cost function even can be a comparison oracle, some box that you say, okay, these 2 vectors are coming in, and which one is just better than the other. So we don't need to deal with the cost function. As long as the cost function is some sort of convex, we can use that. Let's say in this case, the cost function is a capital budgeting problem, a linear term, a root square term, and then this is close to basically very applied test in applied cases in the finance. The size of the problem is around 50. The problem is combinatorial. Basically, the variables are 0 and 1, so that the gray basis that we needed is between +1 and -1. We don't need all the gray basis. When we are extracting this, if the problem is between 0 and +L, then we need the plus and minus L gray basis length. So this is, as I told you, when we solve the problem AX equal to B, we want to find the feasible solution. We end up to many feasible solutions. In this case, we have 6,500 feasible solutions in one call of the D-Wave. And as you can see, even the minimum solution is around -0.5, but the global solution is -3.69. It means that in any of these feasible solutions, when you reach start, you end up to this global solution in some iterations, some limited number of iterations. This is another case which basically the variables are between plus and -2, and still we have the same situation, but we have to call the gray basis 2 or 3 times, the D-Wave 2 or 3 times to find all of the gray basis. Later on, we find out that if we just call D-Wave once, and we end up with a partial amount of the gray basis, and instead of starting from one feasible solution, we start from multiple feasible solutions, meaning all of those feasible solutions that you could see in this thing. Then, even though we don't have all the Graver basis elements, but we reach to classical, to global solution in many of them. Around 8% or 9% of this, the solution in this case is optimal solutions. And we can reach to all of the optimal solutions, not just one. If the problem is degenerate, then we can have all of them. So, the question is how we can surpass the classical systems. One of the suggestions that we had was that increasing the coupler precision, because when we increase the parameter length of the matrix A, we could see that the number of the distinct values of Qij that is needed is increased. So if we have better coupler precision, we can solve better problems. With the same D-wave that we have and the same 50 size problem, we can, if the coupler precision increases by 2 bits, we can surpass the Gurubi problem. And on the Pegasus also, we can improve the solutions by, on the binary problems, we can improve the problem when on the problem sizes between 120 and 180, because the promise is that we can have a complete graph up to size 180. And also, any order of magnitude increase the maximum number of anneals per call in this type of problems helps us, because we just need many of the degenerate solutions in this specific case. So, based on this idea that we had, we created a classical optimization problem inspired by this quantum optimization problem. We call that gamma, and a paper regarding this is coming. I'll ask Professor Tayyur to come and talk about our group a bit, and possibly the gamma.
Sure. I know we have 2 minutes. First, thank you for inviting us to speak here. I wanted to spend a couple minutes because you might be shocked to see a business school professor come into a physics conference. Did I lose my way? No. I started the group 2 years ago. I am a very classical optimization person. For 25 years, I've built classical optimization methods. I started a software company called SmartOps that I built and I sold to SAP, which is a German company. So thousands of inventory problems around the world in global 2,000 companies run off my software. So a few years ago, after I sold the company, I asked, what else can I do with my life? And I heard there was something called quantum computing. And I thought maybe there is a way of beating my own classical methods by some quantum methods, okay? And so I want to see if I can create a second software company that will beat my own first software company. So to that end, we built a group here. We started with AQC thanks to NASA. I think Davide and a few others are here. They have a program where university professors in the US can get free access to the D-Wave machine through NASA. And then, of course, since then, I've been working with the D-Wave directly. I think Denny is here and a few other people. But over time, we started moving also to gate model, since IBM and a few other companies have a different architecture looking at it. What we want to bring to the table is new kinds of optimization methods, because I am a 25-year veteran of classical optimization. A lot of the times I see the optimization method you're using, you are unaware of a whole body of literature like test sets and things from geometry of numbers that some of us are aware of. So I'm hoping that this would be a very good mix where I can learn physics from you and maybe you can learn some integer nonlinear optimization from me. My final interest, of course, is in solving real-world instances. Hedayat showed a simple example in finance. I can also bring a second piece to the physics community. For those of you who are interested in commercializing some of your ideas, where do my PhD students go and work? They are the ones who run Credit Suisse kind of quant organization. So if you go and say, who works on Wall Street? Where do those PhDs come from? Some of them are actually my PhD students. Similarly, there's another PhD student who is doing a summer internship at NASA, who is a chemical engineering PhD student from CMU, who has real problems from ExxonMobil and Dow Chemical that I think can benefit from improved solutions that are not entirely classical. So I just want to take this couple of minutes to introduce the group. Feel free to meet me and Hedayat after the session for coffee. I'm also a guy who drinks a lot, so anybody who wants to see me drinking can meet me at 6 o'clock at stage 12. I'll be at the bar. Okay? Thank you.
Thank you. Any questions?
Okay. Thank you very much. Are there any questions about
I don't want to stop you from coffee, but go ahead.
So in the results that you presented that you already ran on the D-Wave, did
Yes.
you perform a comparison to the kind of tools that we use in this community, such as simulated annealing and its variants?
We compared the whole algorithm with the Groovy.
So for those who don't know, Gurobi is the best-in-class commercial classical algorithm that companies use. So what we did in this paper was compare this with Gurobi. But what may be worth comparing are other methods that are not Gurobi to see what could be a classical or semi-classical method. But in this paper, we only compared with Gurobi.
What I meant was, in terms of the solutions that were returned by D-Wave, those, right, did you compare those to simulated quantum annealing, simulated annealing, parallel tempering, and so on?
No, we didn't.
That's a good
that.
point. I'm now getting emails from people who have different icing solvers and different ways of solving that to say, if you are reforming your problem as an icing solver embedded inside a classical loop, D-Wave is not the only icing solver. I think you're going down that way. And maybe other icing solvers, approximations could be used and as a plugin. We're actually looking for partners who provide that. And Peter McMahon, I think, is one of the Stanford guys going to Cornell. And he has an optical annealer, and he wants to provide, I suppose, a black box that provides output. So that's a very good point, actually. If you have other icing solvers or other ways of solving what we have formulated, then we can plug and play and see, do they give better kernel elements, right? First time around. I think that's where you're going with this. Yeah, very good session.
We passed him some instances.
Yeah.